Can everybody hear me up there? Are we good? All right. So last time we talked about the efficiency of algorithms, the objective of minimizing space and time as we compute. We talked about asymptotic notation, big O, invented by Knuth. That asymptotically captures the growth of the space or the time or whatever other resources we consume while we compute. That's an upper bound, big O. Similarly, we have omega. Those are lower bounds, asymptotic lower bounds on running times or space consumption or whatever else. By the way, these are not restricted to algorithms. Big O, omega, theta, little o, these apply to arbitrary mathematics or growth rates, not necessarily even to do with algorithms, but they come in very, very handy in algorithms. Talked about loose bounds where it's big O, but not omega. We talked about exact bounds, theta, and some growth laws. We talked about solving recurrences. We won't harp on that much. The proof for this master recurrence theorem is in the book. It comes in pretty handy when you have some tricky recurrences that you're trying to figure out what the asymptotic growth rate of them is, but have trouble. This can come in handy. Stirling's formula approximation to the factorial. Basically, it's n over e to the n. That's a dominant term for the factorial, asymptotically speaking. You'll see in just 10 or 20 minutes why it comes in handy, especially in lower bound proofs. And we talked about data structures, lots and lots of data structures, hundreds of them, in fact. The important ones we highlighted in red, and we'll talk more about specific data structures as we go. We talked about arrays, long time to add, because you got to move everything down, but quick if it's ordered. So you can do binary searches if it's ordered, and in log n time find what you're looking for. Yeah, but other things take longer time. So instead of quick adds, unsorted, it takes a lot of time to add to a sorted array and so on. Stacks, last in, first out. Queues is first in, first out, and they both have a lot of uses in computer science in general, and in algorithms in particular. Linked lists, everything points to its logical next structure, and you can have them double linked lists, and searching takes a long time, but adding and deleting a node, if you know where the node to be deleted is, if you have a pointer to it, can be done more quickly. We mentioned a problem for extra credit. If you have a pointer to a read-only list, it's very long, but you don't know how long. You're trying to figure out if it's a nice long list with an end point, or if it's a circular list that doubles back on itself and creates a cycle. Those are the two options, but you don't know which, so you have to come up with an algorithm to determine which is which, and do it in time proportional to the number of nodes in the list, and no extra space, constant amount of extra space, asymptotically only a constant amount. How many solved this problem? Okay, that's good. How many worked on this problem? I hope it's all of you. Any thoughts about how to solve something like this? What's a good algorithm that satisfies this criteria? Time proportional to the length of the list, but only a constant amount of extra space at most. Well, before we do that, let's talk about algorithms that don't satisfy this criteria. Some brute force, naive algorithms that will work, but don't necessarily meet that time and space constraint. Yeah, basically store all the pointers in some array, and if you ever hit a node that you already seen before, you know it's a circular list. Otherwise, you keep going until you reach the end, and then you'll know. What's the time of this algorithm? You just keep storing away, and you're wasting a lot of space, by the way. You're almost doubling the size of the list. What kind of a data structure are we talking about if you want to store all these copies of all these pointers? You can use hash tables. You can use other things. But let's say use hash tables. What's the worst case time of this algorithm? Just cache away in the hash table all the pointers you ever see, and if you ever see one again, it'll be a collision, and you'll know you've seen it, and then you'll know the answer. Big O of n. How many agree? Big O of n, this algorithm. Let me say it's worse than that. Yeah, a few people are saying it's worse. Why is it worse? Yeah, you need to search a table over and over and over again. How long does it take to insert something into a hash table? We haven't talked specifically about hash tables, but I assume most of you have seen it before. We'll talk more specifically about it, and we'll see some interesting hash table tricks. But for now, how long does it take to insert something into a hash table? Worst case. Let's say it's size n. Worst case could be n, actually. It could be a very crowded table with almost no parking spaces for your data. So you have to march, keep driving down the street to find a parking space. You've seen that situation when you try to park, actually. Right? Parking down a long residential street is like a hash table. How many get that? You're trying to fit your car in one of the bins on a parking spaces, and you may have to drive a long ways. Right? In the worst case, you may have to drive all the way to the end of the street, or many, many blocks, or even miles, in case of crowded cities. All right, so that won't work. So what's the time complexity of this algorithm? If you try to insert everything into a hash table and then look for a collision, what's the overall time complexity? N squared, and that's terrible. N could be a trillion, and so trillion squared will never finish on any reasonable computer. Okay, what else can you do then? Yeah. Well, there's only one list, right? I give you a pointer to a list, a single list, and I ask you which kind is it, the first or the second, and you need to tell me. There's only one list. Yeah. Or by the way, if you're here, I'm saying you can't. It's a read-only list. You can't modify. It's unmodifiable. If you can modify the list. Yeah. Okay. And you're right. Those who didn't hear him, well, what do you say? Now let's go for the gold here. ON, linear time and constant space. Because if you could modify the list, you can mark where you've been. This is an extra storage space or a bit for every node. You can, like Hansel and Gretel, with breadcrumbs, mark where you've been, and if you ever go there again through a circular route, you know you're there because it's marked, right? But that's why the list is read-only. You can't do that. I wouldn't ask you a question that obvious if, insult your intelligence by asking you something that obvious. Yeah. Okay. Any other thoughts? Well, I'm deliberately not repeating what they said because I don't want to give it away yet. I'm giving you a chance to say something similar or something different that still works. Yeah.
Is it like a null pointer at the end?
Yeah, at the end, let's say there's a null pointer on this kind of a list. On this kind of a list, there's no null pointer. Everybody just points to something else.
And you just check. Or do you know the size of the list?
No, you don't. Yeah. Remember, unknown number of nodes. That's why I highlighted in a special color, because that's important. If you knew the size of the list, again, the algorithm would be very easy. What would be the algorithm if you knew the size of the list? Just go through it and keep counting to that size, and if you exceed that size, you know you're on a cycle. But again, I wouldn't insult your intelligence by asking you something that obvious. In an undergraduate course, yeah, we'd ask that too. But this is much more subtle. So what else can you do? And I heard a couple of good ideas, but I'm deliberately asking other people to say stuff because most of the class may not have heard or followed what was already said. But there were some nice ideas, him in particular. Yeah. Yeah. Yeah, it's a nice idea to try to limit the number of times you go around a cycle, but how would you do that? Because you can go round and around. The cycle could be 3 nodes, or it could be a trillion nodes, and how would you know the difference? Unless you're storing everything away, which you can't do because you don't have extra space. Yeah. You could. How would you get one to loop the other? Yeah, and a couple other people said it too. So you start 2 pointers, right? You start 2 pointers, So one pointer, another pointer, and you keep advancing them, and you advance one pointer one at a time, and you advance the other pointer two at a time. In other words, the two pointers begin to do this. One is moving twice as fast as the other. If the list is of the first kind, what will happen? One will reach the end, and when it does, you don't care what the other one does, you're done. If it's a cycle, they'll keep going around the cycle at two different speeds. One twice the speed of the other. One will jump one pointer, one will jump two pointers every time the other guy jumps one. What will happen if they end up around a cycle? They'll meet. One will lap the other, overtake it, go around faster, and meet it on the other side. Just like two race cars, one faster, it will overtake the other and overlap it, lap it one more time around the track. And then you'll know. How much time have you spent doing that by lapping it? Big O of n. Not n squared, not n log n, n. The slower pointer will make one lap around. The faster pointer will make how many laps before they meet? At most twice. That's still order n, because instead of n, it's 2n or 3n. That's still n. Beautiful thing about asymptotic notation, it ignores constants. And that's it. That's the algorithm. How much extra space did we use? 2 pointers, constant. And that works. And that's beautiful, it's subtle, it's interesting. Do you have to go speed 1 and 2? Could you go speed 1 and 3? How many say no? How many say yes? Wow, split vote. Why no? Maybe the fast will jump over the slow and never actually hit it. What do you say to that? There's a way to fix that. Still within constant space. How would you prevent the pointer from jumping way over the other pointer, never actually colliding with it, not knowing that they overlapped? What kind of checks would you add?
Well, I mean, you move a pointer 3 times in a loop. You need to move it next.
Yeah.
You check it after each next.
Yeah. So when you move 3 or 4, don't just move 4 and not look at the other one. Move 1, look at the other one. Move 2, look at the other one. Move 3, compare it to the other one. Move 4, compare to the, and one of those will match, and then you'll know. So when one pointer jumps the other, it doesn't really jump it. Slowly overtakes it one at a time, and you can check each time, and you're still good. So that will work. Or you can store all 4 pointers if you want and compare, but that's not necessary. So both solutions would work. 2 times the speed, 3 times the speed, 5 times the speed, as long as it's a constant number. And we can debate whether it's a little more efficient, a little less efficient, but any other thoughts? I understand this completely now. And when you solve a problem, or when you see the solution, especially if you didn't solve it, but see other person's solution, ask yourself, why didn't I see it? And it's not because you're not intelligent. You are smart. But there's some subtle mental blocks, some mental assumptions, and kind of constraints that your brain puts on itself that prevents you from seeing something that later becomes very obvious. It's true all over life, not just in algorithms. Sometimes when you're older, you say, I should have seen that coming. I should have seen that. It was so obvious. Well, it wasn't obvious at the time. But ask yourself, why wasn't it obvious at the time? And what can I do better to make future things more obvious in the present rather than in the far future? And then your life will be better for it. And certainly your problem-solving abilities will improve. Do kind of a post-mortem analysis on your own thinking, kind of metacognition, and ask yourself, why didn't I see it? What was in the way? What, was I assuming something that wasn't true? Was I not getting something that was true? The book Polya, How to Solve It, carries you through dozens of these kind of thinking metacognition exercises and getting you to be a better problem solver. How many started reading Polya, How to Solve It? Just 4 or 5 of you. Okay. If you read it, you'll be much better at solving problems like that and much better at impressing interviewers when you apply for jobs in Google and Facebook and Tesla and other high-tech companies that want you to be able to think fast on your feet. So, if you're not reading those books, especially that one, I'm not sure what you're waiting for. Don't do that to yourself. Yeah.
How long do checking processes take?
How long does a checking process take? Every time you advance a pointer or 2 pointers, how long does it take to check a pointer or compare 2 pointers together? It's a fair question. How long does it take to compare 2 pointers? Constant time. A few CPU cycles. It's a primitive operation. It's not some sort of a loop or anything like that. Pointers are basically addresses. Addresses are fixed locations in memory, either 32 bits or 64 bits on 64-bit processors, and that's it. You compare 2 64-bit quantities for equality or non-equality. That's fast. Yeah.
If the number of nodes were infinite, does this become halting problem?
If the number of nodes is infinite, does it become a halting problem? 2 things. One is the number of nodes is not infinite, it's n. Okay. So n nodes, and n is an integer, so integers are not infinite, right? Infinity is not an integer, by the way, right? How many understand that infinity is not an integer? It's not a natural number. How many understand that? How many can prove that? Prove to me that infinity is not an integer, since you mentioned it. What's the proof like?
If you give me a number that's infinite, then I can prove that infinity is not an integer.
So assume n was infinite, right? So n plus 1 is also infinite, but that's equal to the first n, which is infinite. And so now subtract n from both sides, and you get 1 is equal to 0. That's a contradiction. So infinity is not an integer, because I meant to write with this. So if infinity is an integer, infinity plus 1 will also be an integer, the same integer, because both are infinite, and that would imply that 1 is equal to 0. Okay. So n is a number, it's not an integer. Yeah.
So follow-up question on this proof. How can we say that n plus 1 would be n? Because didn't somebody prove that there are smaller infinities and bigger infinities?
Yes, but you can also show that any kind of infinity plus 1 is the same type of infinity. Let me prove that to you, since you asked. You have an infinite hotel with an infinite number of rooms. Right? The rooms are numbered 1, 2, 3, 4, 5 to infinity. There's no largest room. All the rooms are full of guests. There's a guest in each room. Infinite hotel, infinite number of rooms, 1, 2, 3, all the way out. Each guest is occupying a room. The hotel is full, business is good. One more guest comes in the lobby. You're the hotel manager. What do? You need to accommodate that guest. Can't send them away. How many understand the premise? Okay, no, only a few. I'll ask again then. Infinite hotel, infinite number of rooms. Room 1, room 2, room 3, room 4, room a million, room a billion, room a Googleplex, and so on. All the way out. No end to the rooms. All the rooms are full, a guest in each room. It's peak season. It's like Miami in the winter. A new guest comes in the lobby. You're the manager. The guest wants a room. What do?
So I already have infinite number of guests, and infinity, that's why it's also infinity. I still have infinite number of guests. I can still accommodate them.
Okay, so he says you can still accommodate them, but my question is, what room will be assigned to that new guest? What's the room number?
Infinity plus 1.
Infinity plus 1? So where is that guest going to go? Down an infinite hole and never get to his room? Put the new guest in the first room and move the guest from the first room to the second room. Guest number 2 will move to room number 3. Tell all the guests, move one down. That will free up the first room. Then you get room number 1, and everybody still has a room that's 1 more than their previous number. There's no room infinite. There's no room number infinity. How many get that? Infinity is not a number. There's room number a googolplex and a googolplex factorial, but no room number infinity. It's just an infinite number of rooms. So I just showed you how infinity plus 1 is still infinity. The same infinity as before. Since you asked. Very good question. Very subtle question. Your Cantor, when he started having these insights about transfinite arithmetic, which he invented in the 1800s, his contemporaries didn't think it was real math. By the way, what we just did is a one-to-one mapping between a set and a proper subset of itself. How many get that? Most mathematicians didn't even think it was possible. He gave this example of an infinite hotel, and he gave a lot more examples, and that field bloomed, and people didn't accept it for a good number of decades, and they thought he was a heretic and a crazy guy, and eventually he ended up in an insane asylum, kind of really depressed because his peers didn't appreciate him. And only 50 years later did we realize he was the genius that he was, and David Hilbert was one of the main people that realized that and popularized this transfinite arithmetic, and now we use it all the time in all sorts of places. He also showed that the number of reals is not countable. You can't put real numbers in these hotel rooms. That's an impossibility. So you need to show a non-existence proof. That's hard because you need to prove you're not a millionaire on that one. And we already know how hard that is. But I digress. Any other questions? Okay, so if you thought you understood lists, then this would have been obvious. So there's always more to understand about apparently seemingly simple concepts. Nothing is really that simple. And speaking of things that are not simple, remember the maximum subarray problem. So the maximum subarray problem, we have, this I'll use, okay. So we have an array, and we want to find the subarray, contiguous subarray with maximum sum. And we already said there's an n-cubed algorithm for it. That's pretty brute force. Take all n choose 2 beginning end points of the subarray, add them all up, and when you do, you'll know what's the maximum sum, and that's n cubed. How many get that? We mentioned that a couple of lectures ago. Okay. How many worked on this problem? Oh, good, a lot of you. How many have a solution that's better than n cubed? Okay, what's the next better than n cubed? Like maybe n squared? Can anybody maybe describe an n squared solution before we even talk about n log n's? N squared solution to this. Yeah. So you can compute partial sums, right? So you compute all of these sums, all partial sums, 1 and the first 2 and then the first 3 and then the first 4, all the way to all the sum of all n. And now, when you have all the, and by the way, where would you store all these partial sums? Think about that for a second. But once you compute all these partial sums, to get the sum of an arbitrary contiguous block, not necessarily from the starting element, but from an arbitrary element to some other arbitrary element, what can you do? So you compute all the partial sums. Okay. You compute the first element, the sum of the first 2, the sum of the first 3, the sum of the first 4, the first 5, and so on. And if you want to compute, and once you have all those numbers computed, stored in an array, to compute an arbitrary block going from 13 to 27, how would you obtain that sum very quickly? One word. Subtract. How many get that? You just subtract the 2 partial sums. Take the sum of the first 27, subtract them for the sum of the first 10, and then you'd have the sum of the middle 17 that are left between 10 and 27 or whatever. Let's do one subtraction. How many understand all that? All right. How fast to compute all of these partial sums? N squared? I hear n. That's better than n squared. How would you compute all these partial sums in n time, in linear time? Just keep adding. Keep a running counter, right? The first guy, store that sum in an array. Add the second guy, store that sum. Add the third guy, add the fourth guy, add the fifth guy. Because the other ones are already added up. You don't need to re-add them. You already added them. You already did that work. Just leverage that work. And you'd store all these partial sums in an array. And that'll give you a very quick way to, in constant time, get an arbitrary sum of an arbitrary block. Okay, so far so good. So what's the overall time of this algorithm? N squared. Why n squared? What's the algorithm? Yeah, take any ij combination, and in constant time you know the sum between them, and then you keep a running maximum of all these results, and then you'd know what the maximum overall is. Any ij. How many ij combinations are there from 0 to n, or 1 to n? N squared. In particular, more precisely, how many? Just it's n choose 2. Right? Actually, it's n squared minus. Well, let's just say it's n squared, because an element and itself could be both the I and the j. It's not quite I choose n choose 2 because they don't have to be different. They could be the same. So it is n squared. Of course, n choose 2 is still n squared, just a little bit less. Okay, good. So we're making progress. Right now we have an n squared algorithm. That's better. Let's go for an n log n algorithm. Did anybody come up with an n log n algorithm? A few people. Okay. Did anybody come up with better than n log n? Okay. Well, if you did better than n log n, if you did better than n log n, that's also n log n worth of good, right? Because you can always slow an algorithm down deliberately. It's hard. The hard part is to speed it up. Okay, so only a few of you did n log n. How would you do n log n? I'm looking for a subarray of maximum sum. And it may be anywhere. This is, okay, it's visible. Getting some reflections, that's okay. All right. Yeah, try doing this in PowerPoint. Okay. We're going for n log n. How would you do it? Okay, split the list in half. Because n log n kind of smells like recursion, right? It smells like divide and conquer, and vice versa. It's kind of a, it's not always the case, but often it is the case. So we're going to divide it into two pieces. So we'll do it this way. Divide it into two pieces. And then what? Following divide and conquer kind of intuition. You divide it into two pieces, and then what do you do? Typically, divide and conquer. What do you do with the two pieces? Solve the two pieces. The same problem, right? So find out where the answer is for the first, and where the answer is for the second piece. Let's say these two blues are the answer for the first and the second, respectively, separately from each other, right? But, and then what do you do? Take the best of the two, but there's a third case that may be connected. The answer could straddle the middle somewhere. How many get that? So it's not just the left and the right. The answer could straddle the middle, not necessarily evenly, could straddle the middle any old way. But how would you compute the middle answer quickly when you recurse back up from the recursion? So you recursed, you subdivided and trying to conquer. Better than divide and surrender. You divide and conquer, right? So you solve both subproblems, and it could be the left, it could be the right, but it could be the middle too. How do you obtain the middle? That's not part of the divide and conquer. Well, it's part of the conquer, but not part of the divide. How would you obtain the middle solution that may straddle the middle efficiently, given that you suspect it may do that? It's not hard, but it's not automatic either. It's not for free. How would you do it? Solution for what? Yeah, so first of all, let's back up. How fast do you need to compute this middle solution for the divide and conquer to work in n log n time overall? How much leeway do you have? Do you need to solve in constant time, log time, longer, and still be okay with n log n overall time? Think about like something like merge sort as a template. Merge sort, how does it work? You sort both sublists, divide into two equal sublists, sort both sublists, and then combine them. How do you combine them? How fast can you combine them? How much time do you have to combine them before things go terribly wrong with respect to the overall time complexity? You have linear time to do that merge step, right? How many understand that? You don't have to rush it. You have to be reasonably efficient. You can't take quadratic time or cubic time or n square root n time, but you do have linear time leeway to combine the two answers. And the same here. You have linear time leeway to figure out this middle green solution there. But still, how do you compute it in linear time? Start from the middle point. Find the maximum sum to the left, and the maximum separately. Find the maximum sum to the right. And what's the green solution? The sum of these leftmost sum and rightmost sum, add them together, and that's the best sum that crosses the middle. How many get that? Okay. Think about it, convince yourself that that's true. How fast can you do all that? Find the biggest sum going to the left from the middle, and the biggest sum going to the right from the middle, and then add the two up. How fast is that? Big O of n at worst. And then you'll know the middle solution. It straddles the middle. So we just returned from the recursion. We did some sort of a merge kind of thing. And now what do we report to our parent subroutine that called us to begin with? What do we return back to the recursion? The maximum of the three. How many see that? Because recursively, the solution is either all to the left, like this guy, or all to the right, like this guy, or straddles the middle somewhere. And that's the only three places it can be, generically speaking, in terms of a template general property of where it is. Strictly to the left, strictly to the right of the dividing line, or straddling the line. There's no other place for it to be. And you've covered all three cases. And the answer is, whatever was the best, send that up as your answer. How many see the algorithm now? That's the entire algorithm, basically. It's divide and conquer. Solve both halves, and separately solve the one that straddles the middle by going to the left, going to the right, linear time. Add the two pieces, and then see which one is the best. It may have been the left. It may have been this left one, and then you don't have to worry about the other two. It may have been the right one, then you don't have to worry about the other two. It may have been the middle one, and then you don't have to worry about the other two yet again, and you return whatever was best, and you keep going. Overall time complexity is what? N log n. Okay. Any questions about this algorithm? It is more clever than the other two. Sure. It's also more efficient. So now we're back to, oops. We're now to n log n. Did anybody do better than n log n? How many did better than n log n? Okay, we got maybe two people, 3 people. Good. And that's the next question to you. Can you do linear time? And since only, how many really tried hard to do a linear time algorithm for this? Okay, only a few, maybe 10 or 15 people. It's not enough. So I'll leave it up to you. Still extra credit. Try to beat n log n, and now you know the hint. Try to do linear time. And you already have a lot of hints, and the hints are right there. They've been there all along, but in particular, refine this algorithm even more so it works in linear time. And when you do see it, it'll be beautiful and simple. It won't just run in linear time, it'll just be a few lines of code. Not double digits lines of code. This one is double digits lines of code. How many can see that? It's a few dozen lines with the recursion, and look in the middle, there's loops, and it's going to be the linear time algorithm. It'll be maybe four lines, no more, 5 most, something like that. The single digits. So not only will it be very, very fast, it'll also be beautiful and elegant. And when you find out what it is, it'll be my gift to you. Any questions so far?
Do we just store the start and ending digit of the sequence?
You can store some stuff, but you have to be careful. Make sure it's general, that it works in all cases.
No, I mean, the output, is it required we just output the largest number, or the largest number and where the largest sequence and where you start, where you end?
Oh, I see. He's asking, do you have to report the actual block or just the sum of the digits in the block or the numbers in the block? Yeah, good question. They're sort of equivalent. If you can do one, you can do the other. Yeah, you can yeah. Yeah, if you know the sum and you know it's the best sum, you also know how you got the sum, and you know the I and the j that created that sum. Yeah, the sum is unique. The I and the j may not be unique, but you report whatever, something that works. So they're basically equivalent. But so it's a good question. My short answer is if you can do one, you can do the other very easily. So it's not a big differentiator or anything like that. It doesn't make it harder or easier. It's equivalent. Any other questions about this? So there's still extra credit here, bounty. And I urge you all to work on it. Extra credit. Problem solving is not a spectator sport. If you don't practice a lot, you won't get better. It's easy to fool yourself, though. Okay, so other things we talked about are trees. We said you can have binary trees and you can have height balanced trees. And when you have height balanced trees, it preserves the height being the log of the number of nodes. So adds, deletes, even searches are all very quick, logarithmic time. And there's lots of types of height balanced trees. Height balanced trees, you can have AVL trees. And if you have AVL trees, again, similar technique. There's basically rotations around nodes as you add and delete stuff. Any questions about any of that? So you can have search trees that work in log time per operation. Insert, delete, search. And that's good to know. You don't necessarily have to remember all the details of how to do rotations and all that. That's just implementation details, and some of it is not pretty. And AVL trees have like various special cases. I wouldn't worry too much about it. Just so you know, self-adjusting trees have this property. Any questions? So when you construct algorithms, you can just postulate some height balanced tree. Say it works in log n time per operation, worst case, and you're good to go. When you actually have to implement it, I assume that you can take care of all the gory details. If your life depended on it, you will survive that situation. But we won't harp on these kind of minutiae here. Okay. Tree traversals, you can have pre-order, post-order, in-order if it's a binary tree. And you get 3 different sequences out of these things. I assume you've seen these kind of stuff before. How many have seen pre-order, post-order, in-order? Okay, so you know what I'm talking about. We won't spend too much time on it. These show you the in-order, post-order, and pre-order very nicely, the order in which they're visited. Pretty intuitive. And then heaps, we mentioned heaps, but basically it's a tree where it preserves a heap property that everything below you is less than you. That's a max heap. Min heap is everything below you is greater than you. But the point is that the max element is always at the root. And in every subtree, the max element is at the root of that subtree. So that's just the ordering property. So it's not a total ordering, it's a partial ordering. But the partial order that's being preserved is everything below you is smaller than you in terms of value. And as you add stuff to the tree, it kind of propagates, and you can use a kind of a height balanced tree structure to store the heap. So heap and height balanced trees are kind of interact with each other in terms of if you can implement a height balanced tree, you can use it to also implement a heap, and you get all the properties of a heap. So the operations are very quick to find the min or the max. It's always at the root, so you know exactly where it is. It's the root of the tree always, the min or the max respectively. So without loss of generality, we'll just talk about max heaps. Let's say what's maximum in the root, not the min heaps. To add, again, log n time, because it's a height balanced tree that's implementing the heap. To delete, also log n time. To search is actually a long time, because to search, you have to look at the entire heap, because the heap is not totally ordered, it's partially ordered. So just because the max is up there doesn't mean that the min is any particular place. It could be anywhere in the tree, actually. And vice versa. So to search for a particular value, you don't know where it is in the tree. It could be lots of different places. And in the worst case, you may have to examine the whole tree. So you save on addition and deletion, but if you want to search a heap, takes a while. Yeah, question? What's that?
How we can add order of like n to the heap?
Oh, because the heap is implemented as a height balanced tree, like AVL tree or 2-3 tree or a B tree. So because it's implemented as a height balanced tree, to add, you just find a place where there's nothing below it that's less than it, and it is less than whatever is above it. So to find such a place, all you got to do is keep going down in a tree, and if there's ambiguity, you can go either way. You don't have to go left or right. You can go either left or right. You have your choice. It's a lot of freedom. And then you just keep inserting it there, and eventually you find a place to insert it, and then you insert it there. And because insertions on a height balanced tree is log n, insertion on a heap is log n.
I was thinking maybe heaps is not generally is not balanced all the time.
Well, so technically speaking, a heap is not associated directly with the notion of balance. But it can be, and here we are making it balanced for efficient access. So a heap doesn't necessarily have to be balanced. It could be a very skewed tree. In fact, it doesn't even have to be a tree. But it's nice to implement it as a tree. And because if you implement it as a tree and implement it as a height balanced tree, access to it are bounded by log n, because you inherit that property from just height balanced trees in general. In fact, you can implement a heap as an array, actually. How many have seen that or get that? How do you implement a heap as an array? You know, the middle element in the array is like the root of the tree, and all the left half of the array is the left subtree, and the right half of the array is the right subtree, and then you just keep going. An array can give you a very nice natural implementation of a full binary tree. Okay, so you can do it that way if you want, but I'll leave it up to you. You can implement it in lots of different ways. Okay, hash tables. We mentioned those. It's direct access. It involves a hash function, and it takes whatever the object is and hashes it into some key, which is usually a address in the hash table or in memory, and you just put it in that bucket. So it's like a bucketing scheme, right? You treat the memory as buckets, and you put the items in the buckets based on some hash function. The hash function converts an arbitrary thing into an address, into a bucket address, or a memory address, if you will. It doesn't have to be necessarily a memory address. It could be other things. But still, it's a bucketing. And on average, if the hash table is not too full and your hash function is a good one, it just spreads the data around really nicely, almost randomly, chances are no two objects will collide into the same bucket, and then you're good. But if the hash table gets very full or the hash function is not very good, it can create a lot of collisions, even when the hash table is not very full. You have n squared, you have n worst case, because if you use linear probing, for example, which means if you don't find the parking space where you were assigned by the hash function, you just keep driving down the street until you find one. And that's linear probing. You just keep going. And at the end, in the worst case, you may have to drive a long ways to find a parking spot, to find an empty bin in the hash table. My question to you here is, how do you improve the worst case to logarithmic worst case, not linear? And by the way, I emphasize again that the constant time is not the worst case, it's the average case. And usually when we analyze algorithms, and in this course, we'll always worry about the worst case scenario. We won't assume that the universe is good to us. We'll assume there's an evil oracle working to stifle us at every point in the algorithmic execution, and we'll worry about worst case scenarios. As bad as it gets, that's what we need to worry about. Sometimes we'll worry about average case, but only very explicitly. Usually when we implicitly don't mention if it's average or worst case, it's worst case. All right, so how do you improve the worst case to logarithmic for hash tables? How many have some solution? Nobody. Or maybe 3 people. Okay. So I'm glad I asked. So I'm here to tell you, you can implement hash tables in a way that will keep the worst case no worse than logarithmic. And that's pretty good, because the average will still be constant time. That's not true in height-balanced trees. In height-balanced trees, the worst case is what? Height-balanced trees, AVL, 2, 3, B trees. Worst case is what for add, delete? You already said it, I just wanted to say it back. Logarithmic, okay? Log. The average case for height-balanced trees is what? Also log. How many see that? The average case for B trees, AVL trees, 2, 3 trees, any height-balanced trees is also logarithmic. The average case, not just the worst case. How many can see that? Argue why that's true. I mean, let me argue why it may not be true. I'll be wrong, but let me try. I'll say wrongly that the average case behavior for height-balanced trees is maybe log or log squared. Why? Because sometimes it'll be right at the root. Other times it'll be right one level below the root. Other times it'll be maybe 2 levels below the root. And occasionally it'll be all the way down at the bottom, log n away from the root. But the average might be not as bad as log n. It might be constant. Could be very close to the root. Or the square root of log n. Or log of log n. Or log n over log n. All these are smaller than log n asymptotically. I'm giving you a lot of false leads here, emphasizing on the word false. Why is that all false?
Directly, most of the nodes are at the bottom, right? At the last level.
Yeah, he's saying most of the nodes of a height balanced tree are at the very lowest level, at the leaves. How many understand that? True statement. What portion of all the nodes are at the bottom? Let's say it's a full binary tree, perfect binary tree, full. Half. How many see that? Half. Half the nodes. So on average, half the nodes will take log. Doesn't matter what the other half take. Even if the other half takes constant time, and they won't, because some of them are right close to the bottom too, one level above the bottom. But if half the node take x, it doesn't matter what the rest of them take. The average will still be x, or worse. How many see that? Exactly. And that's why the average case access to height balanced trees is also log. So this will work better. This will work better than height balanced trees if we can solve this problem down here. The worst case will be log, but the average will still be constant. That's better than height balanced trees, which are pretty darn good to begin with. How many see that? All right, so now solve that, and we'll have something really interesting. Any thoughts? Make the bucket what? Yeah, you can play with the bucket structure. And what does the bucket structure look like? Like, he's on the right track. What do you say? Yeah, make the buckets into trees. What kind of trees? Height balanced trees. Make every bucket a height balanced tree, not a linked list. Because if there's collisions, one other thing besides linear probing is chaining. Chaining means you just create a long chain off that bucket. And if there's a collision, just hang it off a linked list that's hanging off this bucket. And if that list gets long, that's okay, it just gets long. And when you search for something that falls in that bucket, you have to search the entire list that hangs off this bucket. And that could be also up to order n, worst case. All the things can collide in one bucket, and then searching that list, or adding to that list for that matter, or deleting something from that list, could take you order n if there's up to order n things hanging off a single bucket, because a lot of collisions happen. That could happen. It's not likely, but it could. And remember, we're looking at worst case scenarios. So instead of hanging individual values off the buckets, or even lists off the buckets, hang height balanced trees off all the buckets. And in the worst case, if everything collides into the same bucket, it's still a height balanced tree growing from that bucket, and it's still log n worst case to see what's going on in this tree. Add, delete, or search. I'm going to get that. And because it's a hash table, these big trees won't even occur very often. In fact, they occur very rarely. Most of the time, you won't have collisions, assuming your hash function is good and spreads values randomly. Has a good, nice, random spread on the range, no matter what is the domain of it. So on average, you only have individual items in the buckets, and occasionally you have 2 or 3, but you almost never have half the things in the table all hanging off of a single bucket. And if you do, the height balanced tree hanging off of it instead of a list will get you a guarantee of no more than log access time for adds, deletes, and searches, and so on. That's a nice Jedi trick to remember. You can make hash tables better by hanging height balanced trees off the buckets. And you still retain the constant average access time, which trees by themselves, height balanced trees by themselves, don't give you constant time on average. This will. And still have the worst case scenario, no worse than height balanced trees, which is it's a nice option to have when you design algorithms or implement it. There is a bit of a cost here, not serious cost, but it's not completely a free lunch here. What do you pay for? What do you pay for this privilege of having the access time on average remain constant, but in the worst case, no worse than logarithmic? What do you pay? First of all, there's a little bit of a higher constant, right? Because you don't just have an item there, you have a pointer to some subtree, and you have to chase that pointer down, and you have to implement that subtree, and you have to do it the correct way that works for all cases. And so there's a little bit of extra coding work, and chance for being wrong and having bugs and not maybe overlooking some special cases or whatever. So more coding and testing. The code will be a little more convoluted. The constant will be a little higher because now you have to chase down trees, not just lists or not just items in buckets, which are right there in terms of their value. It's a pointer to something else. So there's cost involved in chasing down the pointers, and you pay maybe twice as much for access as in terms of CPU time. Not a big deal if you only want to look up, insert, and delete a few million things. Not a big deal. But if you get into trillions of things, it starts to add up. Like Seymour Cray used to say, a nanosecond here, a nanosecond there. Before you know it, you're talking real time. Who was Seymour Cray, by the way? It's before your time, granted. Maybe I'm dating myself, but you should know, the heroes and pioneers of computer science. Yeah, he's the father of supercomputing. He created the Cray 1 supercomputer in the 1970s. The speed of it was 100 megahertz. Not 100 gigahertz, 100 megahertz. It was the fastest machine on Earth at the time. Cost about $20 million. Needed a special set of air conditioning units just to keep it from melting down. It was so high powered. Your iPhone, your smartphone now is 50 times that speed. But this was the 1970s. Okay. Any questions about this? Yeah.
So a question about the averaging system. So do we, by saying that it's a constant, do we say that the hashing function doesn't grow with the size of the hash table?
The hashing function doesn't grow. It's a fixed function that computes a hash key. Say a 64-bit hash key from any value that you feed it.
But if the number of addresses keep on increasing, doesn't the...
Sure. He's asking a subtle question. He says, does the time to compute the hash function actually grow? And theoretically, it grows a tiny bit if the number of bits in the word grows and grows and grows. So if it's 128-bit, 256-bit words, yeah, but relatively little compared to everything else. And certainly relative to the size of the universe, because 32 bits, 2 to the 32 is what in terms of numbers? 2 to the 32 is how big a number? A billion? About 4 billion, thank you. 2 to the 64 is 4 billion squared. That's really, really huge. 128 bits, that's like 10 to the 30, something like that, roughly. 256 bits, it's about a Google. You can do the math. But a Google is such a large number, it's outside this universe in terms of any physical quantity. How many particles are there in the known universe? The known universe is a sphere roughly 14 billion light years in radius. How many particles are there? Electrons, neutrons, protons, mesons, all of it. How many roughly? How much? Yeah, it's about 10 to the 80 roughly, 10 to the 70 something. It's hard to say because, but it's less than a Google, much less than. It's orders of magnitude less than a Google. 10 to the 80 particles in the entire known universe, as far out as we can see. That's a huge number. It shows you how large that number is, 10 to the 80. So 256 bits, I mean, that's an address space larger than the universe, much larger than the universe. Even if you could write on every single elementary particle a data value, the universe would run out, before you can do that. So it's good to understand orders of magnitude. Remember back to that scale of the universe video. So how many seconds are there in a year? How many seconds old are you? How many seconds in a year? How many seconds in a century? How many have ever thought about that or computed it? I do it all the time. So it's about 31 million seconds in a year. 30 years is about 1 billion seconds. A century is about 3 billion seconds. That's it. So none of us has, 3 billion seconds left. unless you're going to be 120 years old. It's good to think about time in this way, because it makes you spend it in much more wise ways and insightful ways if you realize you know an entire century is only 3 billion seconds. How big is a transistor across? The ones in your smartphone. There's about 1 trillion of them in your pocket. How big is each across? Yeah, a few nanometers, 8, 9, 10, 12 nanometers, depends on the VLSI generation that's being used to produce the chips. How big is an atom? How wide is an atom? Say a carbon atom, how wide would you guess? Transistor, you just told me, is about 10 nanometers. An atom is obviously less than a transistor. A transistor is not going to be smaller than an atom, right? Because a transistor is a bunch of atoms, but not that much bunch of an atoms. It's about 1/3 of a nanometer, carbon atom. So a transistor is about 30 atoms across, right? So that means a transistor, if it's a 30 by 30 by 30 block of atoms, roughly would be a few tens of thousands of atoms. There's not a whole lot more room to optimize in chip design. I mean, there's a couple orders of magnitude left, but that's it. There's no more, factors of billion and trillion like they used to be, in Moore's law. That's why Moore's law is kind of really slowing down, almost stopped. It's good to know these things. How far is Pluto in terms of light years? Just let's wrap our minds, kind of play with orders of magnitude. Pluto, light years, how much? The sun, right? You see the sun every day. How far is it away, light time? It's about 8 minutes. When you see the sun, you see it 8 minutes ago. The sun could be gone by the time you look at it, and you won't know for 8 minutes. The moon is about a light second, second and a half, a couple of seconds. Light can go around the Earth 7 times in a second. How long does it take to get to Mars? Light. And therefore, radio transmissions. You want to communicate with a Mars rover. We have rovers on Mars right now. How long does it take to tell them something and have them send back an answer from Mars to the Earth? Light time. Depends where it is, but roughly, give us. It's about an hour round trip. Pluto is about a day, roughly. Give or take a few hours. That's just the solar system. The nearest star is 4 light years. That's Alpha Centauri, Alpha Proxima, actually. Anyway, just orders of magnitude, you should be very comfortable with them. Watch those videos again and again. And, we talk about questions like hash tables and address spaces and orders of magnitude, and you begin to see what's reasonable, what's feasible, what you don't have to worry about in this universe, and that kind of thing. Okay, any questions about any of this? So, again, this is animation of a hash table, insertions, and the hash table basically spreads out the values over a large, from a large range onto a small domain, but from a small domain onto a large range, but in a way that maps it kind of randomly, so to avoid collisions. You want different values to not collide and clash in the hash table, ideally. Yeah.
So if I push in way more keys than there is buckets, then there will always be O of n to access or O of log n.
Yeah, so he's saying if there's more things in the table than there are spaces in the table, the time will get bad, and that's true. So if the table gets fuller and fuller, like let's say at the beginning of the table has a million spaces, empty spaces, and you keep adding things, and you add 100,000 things, 200,000 things, 500,000 things, and then you add 1,000,000 things, all of a sudden there's no space. Algorithmically, if you're implementing this kind of stuff, what should you do? Very good question. This is a practical implementation kind of question. Let's say you're working for some company implementing some search and storage kind of solution in using hash tables. What should you do?
Double the buckets.
One simple answer, if you can manage it, is always make the hash table bigger, much bigger than the number of objects, the maximum number of objects you expect to go in it. Okay. So if you expect like 1 million things to go in a hash table, make the hash table at least size 2 million or 3 million. So you're never more than half full or a third full or something like that. There's another trick if you can't anticipate the number of items. And you can't, so why not allocate just a trillion, a hash table the size of a trillion, and never have to worry about it? Why not just say make a hash table size of a trillion and not have to worry about collisions ever, or having it be full ever? Because you're only going to have 1 billion objects, and the size of the hash table is a trillion. What's wrong with that solution? You need a much bigger space. 1 trillion bytes is more than most of these machines have these days of RAM. And even disks, a terabyte disk is is a hefty piece of storage already. It's not trivial. And you really want so you don't want to make it too large, way too large, and you don't want to make it too small. So what can you do in a practical scenario? You have a hash table and it's filling up like this. You see, that's linear probing right there. It's trying to find a parking space, and that was a collision. This K is going to go into the next available space. What if the table gets really full? Increase the size of the table. How do you increase the size of a table? I mean, things are already hashed and the table is fixed, and what do you do? Create a new table, make it bigger. How much bigger? Double or triple, something like that. Don't make it 10x, but maybe double or triple. Say triple. And then what do? You have to rehash all the items from the old table into the new table. And when you do that, now you have a new table that's bigger, and that'll take some time. And that's okay. Maybe when the table begins to get near full, do that in parallel on your other core, double the table, start rehashing it, and until, so maybe you can do it, you can shadow the original table with a bigger table, and then get rid of the other table, the first table, and maybe do it that way. But you can rehash into a bigger table. The amortized costs won't be very much. It'll still be constant. But the actual cost when you have to switch to a new table could be high, but you can parallelize that on the side, and that could be okay, algorithmically. Okay, let's talk about sorting. So first, why do we talk about sorting so much? Almost half of CPU cycles, any CPU cycles on any machine, are used to do sorting. Sorting is so ubiquitous, it happens most of what a microprocessor does most of the time. How is that true, actually? Why is a microprocessor doing mostly sorting all the time? Almost most of its waking moments are spent sorting. How is that even true? Where is all that sorting happening? And why? When you open a folder by double-clicking on it on your laptop, the files come up in what kind of order in your window? Random order? Alphabetical or by date or whatever you choose to sort it by. And even when the default is alphabetical, that a sorting operation had to occur right there and then. How many see that? Obviously. If you do ls in Unix or Linux, it gives you the files in alphabetical order. Well, a sort just happened, among other things. Right? When an operating system chooses which process to spend the next millisecond on of CPU time, because it's doing round-robin kind of time sharing among all the processes, it's keeping them sorted in some priority order, and it gives the higher priority ones higher priority. But there's a lot of sorting going on all the time in every system. Okay, so sorting is very ubiquitous, very important kind of operation, so we try to optimize that really, really well. So basically a sorting problem is taking an array of integers without loss of generality, it could be other objects, and then you spit them out in some permutation that's sorted. So really the output is a permutation of the input. So in other words, you're shuffling them around. And there's various ways to sort, and we'll talk about some of them. You can sort insertion sort, shell sort. Some of them are faster, some are slower. We'll talk about them. I'm sure you've seen sorting algorithms before, but we'll ask incisive questions about sorting that you, I'm sure, didn't see before. Some really subtle stuff. So we're here for the kind of deeper, more subtle stuff this time around in this graduate course. So in decision tree models, we count the comparisons typically of the sorting. And let me show you a lower bound on sorting. Sorting cannot occur faster than n log n. We're about to prove the lower bound. It's a short proof, one slide. But we assume that the numbers are all unique. If they're not unique, you can make them unique by sorting on a double key, the value, and then within the value by the original index of the array where that value occurred. So without loss of generality, assume that all the numbers are unique. Because you can break ties by the index of the array where these values occur, even if they're not unique. So there's n factorial different permutations on n objects. How many understand that? Right? The first object can go in n different places. The second object can go in n minus 1 remaining places, and so on. So there's n factorial different possible permutations of n things. And the algorithm has to spit out some unique permutation that's the sorted one. And because all the objects have different values, they're all unique, the permutation that's sorted is unique. Okay? And so in the execution of the algorithm, it has to take some path made up of at least some sequence of decisions, yes, no, or greater than, less than. And every time the answer is yes, you go to the left, right, no, you go to the right in terms of the if, then, else, if, then, else. However, ifs are executed, whether they're in loops or nested or whatever. And the unique execution path will give you the sorted permutation, but there's n factorial of them at the bottom, and they're all different. So to get a different permutation of the input, you must have had a different calculation, a different path in the computation based on that particular input. How many understand that? Then, if the two paths are the same, they'll give you the same permutation. And these are paths, execution paths. This is not a data structure. It's not a binary tree data structure. It represents logically the path in the computation that he said is something less than something else, go if, else, and then based on that do if, else, based on comparisons, less than or greater than. So at the bottom, there's n factorial different permutations which represents outcomes or outputs, and these are the leaves of the tree. And if there's n factorial permutations in the tree, the height of the tree has to be at least a logarithm of the width of the tree. How many understand that? Can't be any less, assuming it's a binary tree. And it is a binary tree because it's less than, greater than. There's only two choices, greater than or less than, if, else. Right? It's not a multi-array tree, it's a binary tree. So the height of the tree has to be at least the logarithm of the width, and the width is n factorial, so now we have to figure out the log of n factorial. And here comes which formula? Stirling's formula that we saw a few slides ago, and even last time. And the log of n factorial is n log n asymptotically. And so any computation that sorts, and sorts correctly in all cases, has to have n log n time to run in the worst case. In some cases, it could be better than n log n, but the worst case is still n log n. For example, if all the input is already sorted, you can in very quick linear time verify that it's already sorted, raise your hands to victory, walk away, and you've sorted in linear time. But not in general, you haven't. Just for that specific case where it was already sorted or maybe reverse sorted. So that's a lower bound. We proved we're not a millionaire here. That's hard to do. That means no algorithm at all in the universe for sorting will work faster than n log n time in the general case. Okay, and that's hard to do. It's a non-existence proof. How many understand roughly what's going on here? Okay. If not, meditate over that. Next time we'll talk about it some more. But there's a lot of sorting algorithms. Here I'm just listing the top 50 or so. The ones in red we'll talk more specifically about. And there's probably another 100 or 200 besides those. So just so you don't think, there's only a few. Before we stop, let me give you a couple extra credit problems. So given n pairs of integers, xi, yi, where there's n of them, and the x's and the y's are all between 0 and n, they're all integers. Okay? And there's n of n pairs, and each member of the pair is between 0 and n. Okay? You want to find an algorithm that sorts the ratios, xi over yi, and do it in linear time. Now, if you want to do it in n log n time, you just invoke any sort, any good old sort, like merge sort or heap sort. But that would be too easy, and I would insult the intelligence with that question. So I wanted to do it in linear time. So n pairs of integers, and you want to sort the ratios. And all the integers are between 0 and n, and there's n of those pairs. How many understand the question? Okay, any questions about the question? Extra credit. So if you think you understand sorting, I'll believe you when you solve this one. Let's kick it up a notch or two from undergraduate level. All right, here's another one. given n integers, find a linear time algorithm to find the majority. Majority is the element that occurs at least n over 2 times. It repeats itself. So if an element repeats itself at least half the number of elements, find me that element. Otherwise, tell me there's no majority. So is the majority unique? How many say the majority is unique if it exists? How many see that it may not exist? It may or may not exist. So, if they're all unique, there's no majority, or not enough of them, there's no majority, like an election. If it exists, is it unique? How many say yes? How many say no? Split vote. Why not? Yeah, if you have n over 2 x's and n over 2 y's, both x and y are a majority. How many can see that? So the majority is not unique. Can you have 3 majorities? No. So you can either have 0 majorities, 1 majority, or 2 majorities. Find an algorithm that gives me the majority, if it exists, and do it in linear time. If you didn't have to do it in linear time, what's a trivial, easy algorithm if you didn't have to do it in linear time? Easy algorithm for this. Not linear time, but very easy.
Store everything.
One word. Use only one word to tell me what your algorithm is. Which word are you going to choose? Because when you have to only say it in one word, every word is important. Even 2 words, every word is important. If you want to take 3 words, be my guest. But what's your algorithm? To find the majority, not in linear time, but very, very easy. How would you do it? It's not a trick question. It's not a hard question. Count it. How do you know what it is that you need to count? Count everything. Hash it. You can do better than that. What subject are we in the middle of talking right now for the last few slides? Sorting. So how about if you sort it? If you sort the objects, where's the majority? It's all contiguous. One block. So you can just scan it, find the number of repeats in the current block. When you reach a block that has at least n over 2, you know you got the majority. So with a single scan, you can eventually find the majority. How many get it? So 2 words, sort and scan. Maybe it's 3 words if your word and is counted as a word. Okay, so sort and scan is your algorithm. Okay, but that's n log n. I want you to do it in linear time, extra credit. So if you understand sorting well, let's see you do that. Another one, find the majority element when you can no longer do inequality comparisons, only equality. Because sorting depends on total ordering. Everything is either greater than or less than everything else. But the majority is still well defined even if total ordering doesn't exist. Only equality, non-equality relationship between any 2 objects. Majority is still defined there. How many get that? Only a few people. Okay. Sorting depends on total order. If there's no total order, you cannot sort. How many understand that statement? If I say sort all of these chairs, what are you going to sort by? Size, weight, color, density, age, price? I don't know. Chairs are not comparable. You can't say this chair is greater than that chair. In terms of what? If I say sort all the people in this class, so what are you going to sort it by? There's no total ordering on all these people. If I say sort them by weight, or sort them by age, or sort them by number of atoms in their bodies, maybe then you can sort it. But if I just say sort people, you're not sure what to do because there's no total order on people. You can't say this person is greater than or less than that person. Numerically, it doesn't make sense. But I can still ask for a majority. There's a certain number of people of a certain kind, like the Republicans, Democrats, Independents, or whatever. They can still make a majority, even though you can't totally order them by sorting. How many get that? So majority is still defined, even though sorting isn't defined. And here I'm asking you to find the majority, and there's no more inequality defined. There's no more total ordering defined. You can only tell if something is equal to or not equal to something else. You cannot tell if it's greater or less than. And majority is still defined, and I still want you to find it. I want you to find it in linear time again. And this time you can't use sorting. Why? Because there's no total order, so sorting is not even defined, much less usable. How many understand this problem? Okay. If you can solve this one, you'll be much better off for it. And finally, given n integers, find the maximum and the next to maximum using the least number of comparisons. And now I'm not talking asymptotically, I'm talking exact number. I'm counting every comparison, not big O, not asymptotically, but precisely. Tell me the exact number of the minimum number of comparisons necessary and give me an algorithm to find both the maximum and the next to the maximum, assuming they're all unique for simplicity. Again, if you can solve that, you will be more enlightened. All right, and those are all open bounty for extra credit. And any questions about any of these problems? So again, we're talking about sorting, and you may think you know sorting, and you've heard about sorting, and you're all comfortable with sorting. Yeah? Well, I'll believe it if you can solve all these 4 problems. Yeah. Yeah, I mean, make it as efficient as you can, because you don't want to use too much time, even though if you limit the number of comparisons, you want to also minimize the time. So linear time, let's say. Yeah. But I want the exact number of comparisons, not big O. Question. Well, you cannot use more space than you have time to use. So you can use linear space if you want, but no more, otherwise it'll take you more than linear time. All right, see you next time.
Excuse me.
Yeah.
I just had a question. In this thing where you change the structure of heap, the heap by including a height balance tree to the changing the structure of the means how you stored the hash tables.
Mm-hmm.
So can we use 2 hash tables? I mean hash tables inside a hash table, so use a different hashing function instead of using a.
Let me turn off the recording. Hold on a second.
Can I just submit? Oh, sorry.